Consider a system taken from its initial state I to a final state F in a thermodynamic process. Let us represent the process in a PV diagram as shown. The process is called a reversible process. If the system and its surroundings can be brought back to the initial states without causing any change anywhere else in the universe. But many natural processes are not reversible. For example, when coal is burnt, it converts to ash and carbon dioxide and in the process releases some heat. Can the process be reversed and convert ash to coal again? We observe accumulation of dust everywhere in our houses. Can the accumulated dust on its own fly away and make the house clean? Not only the processes we have just discussed, but many other processes in nature are not reversible. In fact, we can conclude that irreversibility is not an exception but a rule of nature. Why is it so difficult to find a reversible process in nature? Let us consider a steady flow of liquid through a pipe of variable cross-sectional areas. As the liquid flows through the pipe, it may have different speeds at different points. Let the speed of the liquid at A be V1. When it moves from A to B, its speed increases, say from V1 to V2. The process is reversed and the speed of the liquid decreases from V2 to V1 as it moves from B to C. Hence, the process is almost reversed. The complete reversibility of this process is possible only if the liquid is non-viscous. This means the speed of the liquid is the same at A and C only if the liquid is non-viscous. However, in real life, this does not happen. Because of the dissipative effects due to friction, viscosity, etc., complete reversibility is not possible. As we can only minimize the effects of dissipative forces and cannot completely eliminate them, most processes in nature are irreversible. There is another cause for irreversibility that arises due to the system passing through non-equilibrium states. When the system is passing through non-equilibrium states, we cannot identify the intermediate states of the system precisely. As a result, we can't identify the correct path through which the system has passed, while changing from the initial state I to the final state F. Hence, reversibility of the process is very difficult. However, we have defined a quasi-static process as an ideal process that always passes through equilibrium states. Now, we can write the conditions for a process to be a reversible process. For a process to be reversible, it must be quasi-static. And there must be no dissipative effects. Like a quasi-static process, a reversible process is also an ideal one. For example, consider an ideal gas in a container with a frictionless movable piston. A quasi-static expansion or compression of this gas is an example of a reversible process. According to the second law of thermodynamics, we cannot construct a heat engine with 100% efficiency. So, what is the maximum efficiency of a heat engine? If a heat engine working between two temperatures, T1 and T2, passes through idealized reversible processes, then the heat engine achieves the highest efficiency possible. Much before the concepts of thermodynamics were established, Nicolas Léonard Sade-Carnot, a French physicist, proposed a hypothetical ideal heat engine that works with maximum possible efficiency. A hypothetical reversible heat engine operating between two temperatures is called a Carnot engine. To get the maximum possible efficiency, all the processes involved in the working of the Carnot engine operating between two temperatures must be reversible. Since all the processes are reversible, there will be no dissipative effects. We know that a process is reversible only when it is quasi-static. In a quasi-static process, the system will always be in thermal and mechanical equilibrium with its surroundings. There are two processes in which a heat engine exchanges heat with the surroundings. In one process, the heat engine absorbs heat from a hot reservoir at temperature T1. And in the other process, it releases heat to a cooled reservoir at temperature T2. Since the system must be in thermal equilibrium, these two processes need to be isothermal. There must be two more processes. In the first process, the temperature of the system changes from T1 to T2. And in the other process, the system is taken back from T2 to T1. Since there is no exchange of heat involved in these two processes, they must be adiabatic. The cycle of two isothermal and two adiabatic processes through which the working substance of a Carnot engine passes is known as the Cardinal Cycle. Let us now discuss the sequence of steps involved in each Cardinal cycle. Consider mu moles of an ideal gas in a container with a movable, airtight, smooth, frictionless piston as the working substance. Let the walls of the container and the piston be made of thermally insulated material, and the bottom of the container be made of diathermic material. Assume that the initial state of the system is P1, V1, T1 and is identified by point A in the PV diagram. Note that the gas is in a compressed state because of some tiny weights on the piston. In the first step, place the container on a hot reservoir, which is at a constant temperature T1, and slowly remove some of the tiny weights one after the other, and allow the gas to expand isothermally. During this expansion, let the state of the gas change to P2, V2, T1, which is identified by point B in the PV diagram. Let the heat absorbed by the gas be QAB and the work done by the gas be WAB. For an isothermal process, there is no change in the temperature of the system. and hence the change in the internal energy is zero. Therefore, the heat absorbed by the system is equal to the work done by it. Therefore, for an isothermal process, the work done by the system WAB is equal to mu R T1 ln V2 by V1. Let this be equation 1. In the next step, the container is kept on an adiabatic platform. Now, by removing some more tiny weights, one by one, allow the gas to expand. Since the gas is surrounded by adiabatic material, there can be no exchange of heat between the system and its surroundings, and hence the expansion is an adiabatic expansion. Let us assume that this adiabatic expansion has taken the system from B P2 V2 T1 to C P3 V3 T2, and that this is represented by the BC curve in the PV diagram. For an adiabatic process, heat absorbed QBC is equal to 0, and the work done WBC is equal to mu R into T1 minus T2 by gamma minus 1. Let this be equation 2. Since for an adiabatic process, TV to the power of gamma minus 1 is constant, we can write T1 V2 to the power of gamma minus 1 is equal to T2 V3 to the power of gamma minus 1. Let this be equation 3. In the next step, let us place the container on a cold reservoir, which is at temperature T2. By placing back some of the tiny weights on the piston, allow the gas to compress isothermally. In this process, the system releases heat to the cold reservoir. Assume that during the process, the state of the system is taken from C P3 V3 T2 to D P4 V4 T2. Let the heat given out by the system to the cold reservoir be QCT, and the work done on the system be WCT. Since the process is isothermal, QCD is equal to WCT, which is equal to mu R T2 ln V3 by V4. Let this be equation 4. In the final step, place the container on an adiabatic platform once again and compress the gas by adding small weights one by one. This adiabatic compression has taken the state of the gas from dP4V4T2 to A P1V1T1. The work done on the system, WdA, is equal to mu R into T1 minus T2 by gamma minus 1. Let this be equation 5. As the process is adiabatic, we can write T2V4 to the power of gamma minus 1 is equal to T1V1 to the power of gamma minus 1. Let this be equation 6. in one complete cycle, the work done by the gas W is equal to WAB plus WBC minus WCD minus WDA. Note that we have taken the negative sign for WCD and WDA as the work is done on the system during the compression. On substituting the values from equations 1, 2, 4 and 5, we get W is equal to mu R T1 into ln of V2 by V1 plus mu R into T1 minus T2 by gamma minus 1 minus mu R T2 into ln of V3 by V4 minus mu R into T1 minus T2 by gamma minus 1. On simplification, we get W is equal to mu R T1 into ln of V2 by V1 minus mu R T2 into ln of V3 by V4. Let this be equation 7. We know that the efficiency of the heat engine, eta, is equal to the ratio of the work done by the system to the heat absorbed by the system. The total work done is W, and the total heat absorbed is QAB. Note that heat is absorbed only during the process AB. In processes B, C and DA, no heat is exchanged since they are adiabatic. And in process CD, heat is released. Hence, these three processes are not considered. Therefore, efficiency is equal to W by QAB. Substituting the values for W and QAB from equations 7 and 1, and on further simplification, we have eta is equal to 1 minus T2 by T1 into ln of V3 divided by V4 by ln of V2 by V1. Let this be equation 8. Equation 3 can be rewritten as V2 by V3 is equal to T2 by T1 to the power of 1 by gamma minus 1. Let this be equation 9. Similarly, equation 6 can be rewritten as V1 by V4 is equal to T2 by T1 to the power of 1 by gamma minus 1. Let this be equation 10. From equations 9 and 10, we have V3 by V4 is equal to V2 by V1. Let this be equation 11. From equations 8 and 11, we get eta is equal to 1 minus T2 by T1. Let this be equation 12. Hence, the efficiency of the Carnot engine eta is equal to 1 minus T2 by T1. We know that the Carnot cycle is a reversible cycle. Every process of the cycle is a reversible process. If each step of the Carnot cycle is reversed,